I will talk you through some of the scientific goals that can be achieved with space technologies, and I'll be covering um, an abstract level view of what we do with space technologies. So, in this particular presentation, there will be briefly four major topics. Just give me 1 second, I'll get my presentation. Right. So we'll be talking about four different themes in scientific goals, and these are going to be atmosphere, planetary science, satellites, and exoplanets. Now, these are not really covering almost everything, but these will focus on most of the things that we can understand. Okay. Now, coming forward, I'll talk you through two of those concepts that are mostly used while we build the instruments for space, and then we'll go into those four topics. So the first thing is spectroscopy, and if you are an university level student, you must have already gone through spectroscopy. But what is spectroscopy is basically that if you have a material, right, and if you're incidenting some light on it, that is going to absorb some light and it is going to reflect some amount of light, right? So the material is really specific, and if you, for example, if you have aluminum, it is going to reflect some amount of light in certain wavelengths, and it is going to absorb some amount of light in a particular wavelength, right? So by reading what is the wavelength of light that is getting absorbed and what is the wavelength of light that is getting reflected, you can come to certain sorts of conclusion that what is the material, what is the compound that is there in the particular test that you're doing, right? So this is called spectroscopy. Basically, spectroscopy is meaning that you have a spectrum of light and you are learning what is the material absorbing and what is the material emitting, right? So that is what is shown here, absorption and emission, right? And you can build such spectroscopes even in your home also. That is like a fun project that you can do. What you can do basically is that you can take a cd is basically a diffraction grating, right? And you can incident some amount of light on cd, and it is going to diverge all this light into different wavelengths, correct? Now you can put these wavelengths on, let's say, any mineral, and put an imager, and then sort of try to image what is the wavelengths that are getting absorbed or what is the wavelengths that are getting imaged, right? So this is like a basic camera. Now what you are able to see in the image, I'm just giving you a brief understanding of how this works, is like if you take an incandescent light, the blue spectrum is going to be more, and the diffraction in the red spectrum is going to be more, and in the led it is crisp. Now if you take a cfl, there's a lot of absorption bands that are there because of the elements that are there in the fluorescent lamp, right? So this is something that is a direct result of a spectroscopy. And in laser, there's only one particular wavelength, right? So this is a DIY spectroscope sort of a thing that you can always build in your home with very cheap amount of resources. Now, in space, this is really complicated, and we'll go through the instruments. I'm just giving you an example. The next thing is mass spectroscopy. So when you speak about mass spectroscopy, it is also similar, but what you do is you take a, like let's say you have a five carbon organic compound, and what you do in mass spectroscopy is basically break it, and then you send it through magnetic fields, right? So what happens is this when you break this compound like 5 into 3 and 2, and they have some sort of charge, and you put it through electric fields, they are going to get diverged, and some amount of mass is going to get attracted someplace, and some amount of another mass is going to attracted another place. By analyzing what is the mass spectrum that you have, you can get to a certain sort of conclusion about what is this compound may be, because you know the exact masses that are attracted. So this is called mass spectroscopy. So these are two different instruments. Now let's get into some of the scientific goals. Now we have understood two basic things, that we get to learn a lot about in the coming slides. Now, first thing is atmosphere. Now, in these slides, what I'll be doing is I'll be taking you all through a little bit of scientific concepts, and then we'll also learn about the instruments that we use in space to measure. Now, when we talk about atmosphere, the basic thing we learn from school, there's a lot of layers, and these layers are basically arranged based on the components that are there. In the troposphere, it is highly dense, the pressure is more, the temperature is more, right? And you go through go to stratosphere, ozone is there, the density is less, pressure is less, and you proceed mesosphere, then thermosphere, then exosphere. So here what happens is that in troposphere the temperature decreases as you proceed, but then in stratosphere again the temperature starts increasing, as you can see, minus 56.5 to minus 2.5 degrees. Why this happens is basically there's ozone, and ozone is sort of trying to absorb all different UV radiation, and it's getting heated. Now in mesosphere, it is the opposite. Again, it is decreasing because there's no special absorption that is happening. Again, in the thermosphere, what happens is all the other radiations like gamma rays, right, and cosmic rays, X-rays, all of them get absorbed by very less dense molecules that are already there in the thermosphere. Now, what is the depiction here that I want to focus on is that even if your temperature is like at 1200 degrees in the thermosphere, if you go physically, then you will not feel it because the density is very, very less. So the pressure is also very less. So how do you feel heat is basically by interacting with molecules. If there are a lot of molecules at a particular volume, then you sort of have to feel those molecules, and that's how you feel the heat, right? But when there's low amount of molecules in thermosphere, it's not going to feel like that. So you'll feel a damn cold even though you have 1200 degrees centigrade if you take a thermometer, but if you will feel like you are in almost like minus 200 degrees centigrade. And then you come to exosphere, where you have this exosphere is basically out of atmosphere. You have satellites and spaceships, right? So again, here also it is the same thing. Even though the temperature shows higher, the temperature is not really higher because there's like no molecules there. So all you have is your cosmic microwave background radiation, which is around 4 Kelvin. The radiation pressure that it gives you is 4 Kelvin. Now, why I want to talk you through all of this is because I want you to understand little bit of atmosphere science, because before we go into how we use space, right? So the main thing that when we talk about atmosphere at any particular level of our career is something called as radiation budget or radiation accounting. This image is very standard. What it shows is the incoming radiation. Some amount of it is getting reflected by the atmosphere itself. Some amount of it, I'm talking about the left side here, some amount of it is directly coming and getting absorbed by the surface. Now, the amount of reflected by the surface, right? So this 30 that you are seeing is the main thing that you see in imaging satellites. So when you see Google Maps, right? So what Google Maps show you is the sunlight that is getting reflected out of the surface, right? So this is the amount, this is the particular wavelengths that radiation that you see, and also the radiation that is getting reflected out of atmosphere. The main thing here that you have to also understand is something more that is getting reflected is getting absorbed by the Earth surface. So Earth surface during daytime gets heated a lot. Okay, the one more component is some amount of 67 amount of solar radiation is also absorbed by the atmosphere also. So atmosphere is also acting as a heat sink, right? So heat is coming from the sun and it is getting absorbed by atmosphere. Now we have understood how the incoming radiation gets absorbed. Now we want to understand how Earth's absorbed radiation gets radiated again back. So the first component is thermals. Thermals is where your surface is uneven and your heating is also uneven. So for example, if you have a hill, right? So the temperature on hill is very less, right? So the air is like denser there. And when you come down, there's lot of light, high temperature air, which is lighter. So it wants to go up, right? So heat goes up to the atmosphere in thermals. This is also a phenomenon that gliders use. So gliders, if you have heard of, they don't have any engine in aeroplanes, right? So what gliders use is this thermal phenomenon where the air is going up, so they just stay in the thermal so they can go up without any engine or propulsion. The next component of heating that atmosphere gets is evapotranspiration. Evapotranspiration is basically evaporation and transpiration combined. Evaporation is that the water molecules are getting converted into gas and are heating up the atmosphere above, and transpiration is the water molecules coming from the plants, right, that are getting into gas and heating the atmosphere above. So these are some things that heat the atmosphere. The main component that heats the atmosphere is the surface radiation. So Earth, so like sun is a black body, it emits its radiation because it has a certain amount of heat. Like because Earth has already absorbed radiation from sun, it is also emitting the radiation that it has absorbed, right? So Earth is also a black body, so it is emitting the radiation it has absorbed. Now this is the biggest component that Earth wants to send out, so that is how Earth is warmer from inside. And there's also component of geothermal energy that Earth has internally, right? So Earth's core is like heated, and there's also heat sinks and convection cells that are inside the Earth. They also contribute to some amount of surface radiation. Now, the focus here should be that the surface radiation totally does not go away into space. What happens is atmosphere again acts as a heat sink. So atmosphere is absorbing radiation coming from sun, and is that atmosphere is again absorbing radiation coming from Earth also, right? So it is always acting as a sink, and this has been the case from a lot of years since the atmosphere has formed and the atmosphere has become stabilized after the Earth has formed. This is the phenomena. But there's a critical component in the right side which is called as greenhouse gases, right? So these are gases that are sort of absorbing these radiation that is coming, and because of human activity, the volume or the parts per million of this greenhouse gases, the concentration is increasing, and thereby atmosphere is acting more as a sink, right? It is absorbing more of the radiation and it is sending back the radiation. So what is happening is there is one layer in the atmosphere, one layer in the Earth, and the radiation is doing pinball, up, going down, going up, going down, and thereby heating the Earth's surface. So this is how greenhouse gases are contributing to the Earth's heating. Now, I just want to focus on how Earth's weather happens. So because Earth's temperature is like really ununiform across the heights of the Earth, and also there is water, so the temperature there is cooler. So there is always this difference in pressure and difference in density, and that is how winds move, right? So this is all contributing to weather. So one day there can be high temperature, one day there can be low temperature because of rains. So this is how the weather happens. And this is where we have to understand the concept of weather and climate. Weather is like the short term state of the atmosphere. It all depends on what is happening in the local sense, what happened yesterday, right? And what is making the rain today, etc. And it can change within hours, within days, or within even weeks also. But when you talk about climate is long term pattern of the weather. So if you say that equator, or let's say the tropics, India is in a tropic, so the tropical climate is always hotter than, let's say, longitudes that are more than 35 and 40. So that we are making a statement about Earth's temperature pattern, right? And it is true whenever you take, right? So across thousands of years, it's going to be true, because Earth as a planet is tilted, right? So there's going to be certain sort of patterns, right? So this is called climate. So climate is long term pattern of the weather, and weather is short term state of the atmosphere. Now, this is important because there is a certain observation that has been done, is that temperature is changing in the last 50 years, and the temperature is increasing, right? So as you can see from this image, the temperature is actually increasing all over Earth, and it is more in the near the poles, because what happens is that ozone's density is less near the poles, because and then ozone is the UV is directly hitting where the ozone is not absorbing. So now atmospheric studies mostly happen to understand the composition of the atmosphere, what are the gases that are there, what is the density that are there. And these days most of the research is around the greenhouse effect. As I have already explained, this is the layer between the Earth's surface and the atmosphere, where radiation is doing bouncing from the atmosphere and to the surface. So why this absorption happens, we want to understand, is basically there are molecules, right? So these are certain examples of greenhouse gases: is carbon dioxide, water being a very big greenhouse gas, ozone, nitrous oxide, and methane. What happens is these molecules, they are very much prone to vibration, right? So they can vibrate, they can rotate, they can translate, and in these modes of vibration they can absorb a lot of heat, absorb a lot of radiation also. So in this way they actually absorb this radiation, and we want to estimate what is the component of these gases and also the other gases which contribute to other phenomena. And that is how we want to study atmosphere. Now, if we want to study atmosphere, there are multiple ways to study. If you want to study local phenomenon, what you can do is you can launch a radio sonde, which is like a balloon, helium balloon, and you can attach payload to it, and they are going to sample these things, the gases, and they can give you the data, and it is only going to give a column of the data, and the balloon is going to burst when it goes to stratosphere. The other way that scientists are studying atmosphere is like from space. So what happens is that there are satellites, both geostationary and also low Earth orbiting. We'll see what those are. So what happens is when you put payloads into satellites, they're going to continuously sample this atmosphere, atmospheric variables, both the vertical profiles and also the horizontal profiles, like how ozone is distributed, etc. And thereby we can study a lot of additional information. This is just a slide showing you how many satellites are really focusing on greenhouse gases and how important it is to really come to terms with climate change, right? Because once even a small component of CO2 increasing in atmosphere going to give a lot of heat inside Earth, and that is going to affect both the biology, biosphere, and also our economics. We can also see plants that are going to give less yield when the temperature is increasing, and all sorts of things, right? So that is very important to understand, and this is why a lot of agencies and also even private agencies also have launched satellites that are sampling these gases, right? So you can see CO2, CH4, and how whenever they are launched. So wanted to give you two different examples of how these satellites work. So one of the satellite functioning atmosphere satellites have, most of satellites have scatterometer. So how the scatterometers work is basically they are satellites that are orbiting around Earth, and what they do is they send radiation and they measure the reflected radiation. So it is like they are sending radar waves, and based on the surface texture, the reflected wave either comes to it or not, right? So this is mostly to study wind speeds on the oceans, right? So even in the latest ISRO satellite also has the scatterometer payload. So based on, if so, for example, if there's a lot of wind, there's going to be a lot of waves and a lot of disturbance, right? So the satellite will be able to see bright reflections that are coming. But if the ocean is steady, there's not going to be a lot of reflection that's going to come to scatterometer. So thereby we can understand wind speed, low pressure, high pressure, temperatures, etc. That's one thing. The other thing is sounders, how we understand the vertical profile. So this is the latest research that is happening in the atmosphere research. So what they do is there are already satellites that are there for GNSS or GPS. They are always sending some microwave radiation, right? All in all directions. So what these sounders do is they hover, like if the Earth is in the spherical shape, they hover at the border, right? So they want to understand how the profile is there in the vertical, right? So what they do is they observe these radiations that are coming from these GPS or GNSS satellites, and they see what is the amount of radiation that is absorbed, and thereby they analyze what is the mineral or what is the group, like hydroxyl group or methane group, methyl group, that are there in the atmosphere in the vertical sense. Now, not only GNSS, most of the satellites also observe solar radiation, because solar radiation is spanning all wavelengths. So they also see solar radiation. So these are called sounders. Sounders see vertical profiles. So that concludes our general sense of how satellites, work on observing the atmosphere. Now we will also have some questions. Just give me 1 second. In the later half, we will also have the questions uh, after covering all of this. Now let's come to the planetary science. So this is going to be interesting because now we understood, okay, atmospheric research, it happens like that. Now, a lot of satellites and a lot of orbits and also launchers are launched to understand how planets are formed, what is this planets, what is the life cycle of this planet, when moon has formed, how moon can also help in understanding Earth's formation, etc. So this is all comes under planetary science, and planetary science entails study of planets, study of moons of planets, asteroids, and comets. We'll understand what is all of that. So how they can help us is basically to tell, one thing is planetary geology. So if you understand how a planet is formed, like how Earth has formed and what is the geology of Earth, you can tell a lot about how the solar system has formed, right? So that is one thing. Cosmochemistry is another thing. So if you understand the chemistry of Earth, chemistry of Moon, and solar system as a whole, that okay, solar system is made mostly of this type of component, you can understand ki how the solar system has formed, what was the parent of the sun, because sun is a second generation star, so there was a parent star to form sun, how this has happened, and also what is the cosmology that is happening across the universe. The third thing is atmospheric science. So Earth is a planet like that. Other planets have certain sorts of atmosphere. Mars has a very violent atmosphere. Venus also has very violent atmosphere. There's sulfuric acids and all of that happening in the atmosphere. So that is one thing that you can study. Physics is obvious. Oceanography also, when planets are forming, there's a lot of molten material that is there, right? And even Mars has a little bit of proof of, like, there's like polar ice caps that are there, and there is also on Moon also you can see some things, right? So you can study how this hydrology happened and hydrologic features that are happening across our solar system. There's also interesting features on Titan, that is Mars, Moon, and other moons as well, right? And that is the same for hydrology. Theoretical planetary science here indicates, so for example, if you understand the distribution of mass across the solar system, you can sort of tell how was the breakdown of the solar system that was happening when it was forming, the solar disk, as we call, etc. And glaciology is the study of ice caps, and ice caps actually exist in a lot of moons also that we are actually studying. Now, I want to take you through some examples so that you understand what is happening in the planetary science. One of the good examples that we have is Chandrayaan 2. So we launched an orbiter for studying moon, and that has these particular instruments. And you can see most of these instruments are spectrometers. As I already told you, spectroscopy is a study of what material that is there by measuring its reflectances, right? So some amount of sunlight is coming and the material is absorbing some radiation, and how much amount of radiation is getting reflected, thereby we can understand what is the material. So first thing this Chandrayaan 2 orbiter has is the terrain mapping camera. So this is like a normal camera, like Google Maps, how Google Maps shows. This is also a camera which is showing black and white images of 5-meter resolution. That is standard that you can understand. Chandrayaan 2 large area soft X-ray spectrometer is like spectroscopy you're doing in X-ray wavelengths, right? So X-ray wavelengths, if you do X-ray spectroscopy here, what happens is that most of the X-rays are scattered and absorbed in the upper layers of the atmosphere, as we discussed. So on Earth, it is rare to find the X-rays that are penetrating through the atmosphere, although we do find some of the times, but they are very rare. So on Moon, you don't have any atmosphere to sort of absorb these X-rays. So you can clearly find out what is the amount of X-rays that are getting absorbed by the materials that you have. So X-ray spectroscopy makes sense, and that is the instrument that is there in the orbiter. One more thing is solar X-ray monitor. It is like monitoring the X-rays that are coming from the sun. That is the orbiter that is doing the work. Orbiter high resolution camera is also similar to terrain mapping camera, but it has more high resolution, right? So this is, you can see clearer things. By using both of these cameras, you can actually construct a 3D profile of how the craters look and how moon surface is, the 3D profile. IR spectrometer is basically a spectrometer that is doing its work in infrared range. So infrared is the range of spectrum of the light that happens to have the heat signatures, right? So even water that was detected on Chandrayaan 1 was using this IR spectrometer. So water has a particular absorption band near 3 micrometer. So if you see that, okay, most of the wavelengths that are coming from this moon are getting a dip near the 3 micrometer range, you can conclude that there's some sort of availability of water. And more research is getting done on what is this hydroxyl group actually in, etc. That is one thing. So spectroscopy done in infrared ranges, IR spectrometer. Then there is dual frequency synthetic aperture radars, right? So most of the above things, what happens is that solar radiation is coming and you're measuring the reflectances. Now in radars, what happens is that satellite itself will emit the beams, okay, and it will observe the reflected beams, right? So this is the concept of radar, and synthetic aperture radar is basically simulating a very big antenna from the movement of satellite, right? So how these help is, one thing, radar can penetrate ground also. So if you so in this dual frequency, we have L band and S band SAR. right? So L band actually penetrates the a little bit of the surface also, uh, to from 5 centimeters also, to 1 meter, depending on what the surface is made of. And measuring the reflectance will tell you what is the surface actually made of, right? So that is how dual frequency, that cylindric aperture radar works. And atmospheric compositional explorer is basically, uh, uh, it's like a sounder, and the scatterometer that I told you, it is trying to measure atmospheric composition, but it does not work on the sounder and the scatterometer principle, but it is basically sampling and also observing atmosphere, and it is trying to see what is the amount of radiation that is getting absorbed. The next thing is dual frequency radio science experiment. It is sort of observing in two different frequencies of radio spectrum, and it is basically sending some amount of radio to, like for example, take two wavelengths, right? So there is x1 and x2. It is emitting wavelengths, it is emitting light in those wavelengths, and it is, and on the moon surface there are some absorbers, right? So it is the absorbers are looking at the satellite and seeing what amount of wavelength is getting absorbed. So in these two wavelengths, you can actually see some amount of electrons that are absorbing these wavelengths, etc. So you can then see key, okay, there's some amount of ions that are there in the lunar ionosphere. So these are some of the instruments. And most of the time what happens is that in planetary probes, the instruments are in this sort of way only, right? So even when we see for let's say Mars orbiter mission also, you have methane sensor for Mars. It is also observing planet for certain dips where methane is doing. Menaka is neutral component analyzer. This is also mass spectrometer that we discussed in the starting. Lyman alpha photometer. So Lyman alpha photometer is interesting because you all must have seen the Lyman Balmer lines that we studied, right? So hydrogen is an when you consider hydrogen as an atom, if you excite the hydrogen to the electron in the hydrogen to 2s orbit, and when the 2s orbit electron comes down to 1s level, there's the amount of radiation that is emitted, and it is called Lyman wavelength or Lyman line. So this Lyman alpha photometer, what happens is that you can observe what amount of hydrogen is there in a certain environment, and that is what is Lyman alpha photometer. Infrared imaging spectrometer is similar to IIRS that was there in Chandrayaan, and Mars color camera is a standard camera. So this is from a paper that I have written. You can also read it on ResearchGate. I have just given the links here. Probably the slides will be shared by Spartificial guys to you all. One more thing is the rovers that are there on Mars. And again, if you see the payloads, now I have told you about Chandrayaan and Mangalyaan, you will see that, okay, these are something that are similar. Subsurface radar is a radar that is penetrating the ground, which is called ground penetration radar or GPR. Zoomable panoramic cameras. Panorama, everyone knows these days. You can stitch these images in all different views and form a very big view. Those are panorama images. And zoomable panoramic cameras are these already have hardware to make the surface images for panoramas. MOXIE is an instrument that is there to produce oxygen from Martian CO2 to test whether we can produce oxygen or not on the Martian atmosphere. We have laser micro imager. What laser micro imager does is, like, you have iPhones and you have lidars, right? So when you use laser, what you can get is a 3D information. So on a microscopic level, you can observe how is the texture and what is the material that is made of using laser micro images. Weather station is standard weather station, giving you density, pressure, temperature, etc. You have ultraviolet spectrometer, spectroscopy done in ultraviolet range, and you have X-ray spectrometer, the similar kind that was there on Chandrayaan. Now, we have understood in a broader way of how planets are studied. Now, one more thing is that when you talk about planetary science, you have to talk about moons of distant planets and interstellar voyage, etc. So one of the example is Voyager. So this Voyager is really famous because it was covered in almost all documentaries. This is a probe, and there are two versions of it, Voyager 1 and Voyager 2, that you can see in neon and pink. What these do is basically they use gravity of different planets to go around almost all planets. So you can see Jupiter, Saturn, Uranus, and Neptune were all covered using Voyagers, and we have beautiful images of all these planets, and even Pluto and moons of Pluto also, using these Voyager probes, right? So this is one example of interstellar voyage of man-made satellites. One more thing is we have to understand that solar system is not just made of planets and moons, it is made of lot of smaller materials like asteroids, comets, and meteors, right? So to understand what is the difference, comets are really high radius doing orbits, right? So for example, if you have a comet and if you have an asteroid are groups that are rotating in and around Jupiter, Saturn, and again they are going back, and they have short orbits. Comets have very long orbits, and what happens is that asteroids don't tend to lose a lot of material from them, right? And the composition of asteroids and comets are really different. Comets, what happen is that when they come close to sun, they shed a lot of weight, they send out a lot of material from them, and that's why you see a lot of big tail having comets. And again, when they go far from sun to far distances, even comets there are there near Pluto also. So what happens is they gain a lot of, again, molecules come and attach to comet, and the ice forms again. So again, when they come too close to sun, they lose. When they go far from sun, they gain weight, right? So this is how comets work. And meteors are really small fragments from these comets or asteroids that are coming to the Earth's atmosphere, right? So meteors are a phenomenon that you see in the sky. Meteoroids are those rocks, and meteorites are those rocks that are coming and falling on Earth. Now, in space study, there were also missions that are flown to study comets and asteroids also. One of the example, very famous example done, I think 1 to 2 years back, is Rosetta. So Rosetta has studied asteroids and comets and has actually gone and landed on a comet called Philae, right? So it has, as you can see, it has used both Earth's gravity and Mars gravity to propel itself to an asteroid called as Tains first, and then it went to asteroid called as Lutia, and we have all the images from this Rosetta mission, right? So you can see clearly how these asteroids look, and then finally it went and landed on the comet called as Philae. Now you can see one image here. This is also coming from Rosetta itself. So this is how a comet looks, and in the background you can see how a lot of material and gases are being shed by the comet. Even when it has landed also, it has been given a beautiful picture of a lot of gas that is coming from the surface, and then it has died there. Now if you also study about Rosetta's instrument, most of it are going to be spectrometers in different wavelengths, and also mass spectrometers, and again cameras, right? So that is a standard thing that you can study, because what we want to understand about any comet is that what it is made of, what is the phenomenon that is happening, and what is the chemistry that is there. And you can do that using spectroscopy and in different wavelengths, right? And cameras also, to understand what is happening. And now we have just an overview, because and just to note that these topics are very complex, and I am just giving an overview so that we all understand how space is being used to study all these different topics. Now I want to take you all through this concept of satellites, right? Because satellites, we keep hearing every day, what are the satellites, etc. Now in this I will cover multiple things. First thing is orbit. So satellites can be in multiple orbits. So satellites, when we speak of satellites, these are something that are rotating around a parent body. Most of the time when we talk about satellites, they are going to be rotating around Earth. And there are multiple orbits. Geostationary orbits are orbits that are really far from Earth, in the 36,000 kilometer range, and they, when you place the satellites in those orbits, they are going to be really stationary with the point that is directly underneath them. Low Earth orbits are orbits which is like around 200 kilometers through to 1000 kilometers. And there are orbits which are polar, right? So for example, at one point it is close to Earth, and at one point it is farther to Earth. So how these orbits, satellites are used is basically for multiple things. One thing is communication. So for example, if your dish TVs are there, they are tuned to geostationary satellites. So because the geostationary satellites are always going to be at a single point in space, so once you tune your antenna to that satellite, it is always going to communicate to it, right? And even for example, defense uses, if something happens, right, to our terrestrial networks, right, then you have to communicate through a satellite, and that is how again you will use those satellites. The other use is observation. So observing satellites are like Landsat and ResourceSat. The kind of images that you do see on Google Maps, all of them come from observing satellites. So there are huge cameras or radars that are put on the satellites, and thereby you see different phenomena that is happening on Earth. The other type of satellites are navigation and data relay satellites. So satellites also can be used for GPS, AIS, and data relay uses. So, for example, if you want to send some amount of data from here to America, how do you use the satellite? Is basically when a satellite comes over you, you upload this data to the satellite, and the satellite is going to go to America in, let's say, next half an hour, because it's going to orbit and Earth is also rotating. And then in the next half an hour, it's going to dump all of this data over there. So these are some really fast mechanisms by which you can send the data, and these are conceptualized for other uses also. For example, if you have a human space mission, right? Those space missions are orbiting around Earth. Now, if you want to send those data to Earth, what happens is ground stations are not really visible. So what happens is that space capsule, human space capsule, is going to send the data to satellite, and the satellite, when it comes to the ground station, it's going to dump again the data. So that's how these data relay satellites are used. And in defense, the use of satellites is really wide. There are satellites that are used as weapons. Spy satellites are there in different frequencies. There are satellites which can listen to what we speak also. So there are jammers, etc., etc. So that is really wide. Two different very widely used observing satellites are optical satellites and radar satellites. Optical satellites are, again, just giving a reference of how you see Google Maps, and radar satellites are satellites that are going to emit and absorb the radiation, the kind that we've seen on Chandrayaan. So this is how the difference looks. So in the bottom, what you're seeing is an optical satellite, the wavelengths that our eyes can see. That's why we call them optical or visible wavelengths. And in the radar, what happens is that you send some radiation and observe the reflectance. So it is a black and white image. So this much amount of radiation I have sent, this much amount of radiation I have got, right? So that is really dependent on how the surface looks. For example, if the surface is like this and the satellite is sending the wave, it is going to get reflected in another direction, right? So the surface has to be tuned to send the radiation to the satellite, and thereby we can understand the texture also. So this is also widely used. One of the important uses of radar satellites is that radio waves penetrate through clouds, right? So if you have a lot of cloud coverage, optical satellites can't see anything. All you can see is cloud. But in radar, cloud is not visible because radio wavelengths are actually bigger than how the cloud molecules are arranged. So they penetrate and they finally hit the ground and again reflect back to satellites. So you don't see ground, you can see what is happening on Earth through clouds. That is interesting. And how these all are used in geophysical processes is that, for example, I'm just giving you an example to make you understand how the satellites are used. So if you take optical satellites, right, they reflect a lot of wavelengths, right? So one particular wavelength that is important is called near infrared. And what happens is that if the vegetation on the ground is healthy, it reflects a lot of near infrared, okay, by the physics of the plants. So there are indexes that are built using these wavelengths, right? So some of the indexes are normalized differential vegetation index or enhanced vegetation index. By calculating this, you can predict what is the vegetation health. And if you plot it, right, for example, what we have plotted here is average vegetation index by date for a forest. So you can see that forest health is growing and coming down, and it is very seasonal, right? So if there is a bigger dip, you can understand that some deforestation kind of thing is happening. And if you have a bigger increase, you can see that, okay, there's good rainfall and tree plantation is more extended, etc. and etc. Now this is an example for a forest, and this is the same thing that is done for agriculture also. So you can see how the farms grow, when have the farms been sowed, seed life cycle, etc., etc. So that is how agriculture is studied. So this is one example of how you can study. One more thing is, you can use the satellites as telescopes, right? So what happens is, if you have telescopes on ground, they cannot observe a lot of sky because there is atmosphere and there's a lot of light pollution also. One thing that scientists do is they build huge telescopes and send into space, and then they observe light from space. Then what happens is, there's no atmosphere and there's also no light pollution, and you can clearly observe what is happening in space, right? So these are set of telescopes. One famous telescope is Hubble. The recent one is James Webb Space Telescope. So this is a telescope that does not have visible wavelength. So it observes space in near infrared, such telescope has not existed till, right? So all you can see is that you can see the all the stars in infrared range. I'll also show you an example. One interesting thing about these telescopes is that they have to be really specific, because especially this is an infrared telescope, it has to be specific to the heat, right? So it should not see the sun, because sun emits a lot of heat. Earth also it should not see, because earth also emits a lot of heat, and moon also emits a lot of heat by sense of radiation and reflection. So what happens is that there's a lot of mylar sheets that are placed, like you can see the aluminum foil kind of thing. It's called a mylar. So what happens is that it reflects a lot of radiation, the heat radiation, right? So what happens is that these satellite, for example, James Webb, it is placed in a point called as L2, where heat is from the sun is not there. So for example, you can see in the first image that there are solar panels, and the telescope is looking away, right? So what happens is that if you place the satellites in certain points, this heat from earth and sun never reaches its mirrors, right? So that is an interesting engineering that is done in James Webb. For Hubble, that is not the case, because Hubble actually observes in optical, so there's not a lot of disturbance. But when you have such a huge star near you, there's a lot of disturbance in infrared, and that is why you have to engineer your telescopes to place it away. So these are also some of the satellites that are there. And for example, here James Webb is a satellite for sun. It rotates around sun, it orbits around sun. But for Hubble, Hubble is a satellite around Earth, as depicted in the image. So this is one example of Jupiter seen in the infrared region. This is a near infrared. Here what you can see is, for Jupiter it has the rings also. Like for Saturn it has huge rings. For Jupiter it has smaller rings that you can see. On the left you can see one of the Jupiter's moon. And if you actually Google this image and see, you can also see a lot of galaxies also that are emitting in near infrared. So that's one example that I wanted to share with you, and this is how you can study celestial objects with satellites. One other important thing is navigation. So as you go into deep space, for example, how navigation happens for near space satellites is that there is a standard pattern of star around Earth, right? So stars are always fixed, almost inertially fixed in the stellar space. And if you see certain star pattern, you can actually say, okay, I am at this particular place in space if you're near Earth. But if you go very far from Earth, what happens is that you cannot really understand what is this pattern, where I am, etc., etc. So what happens is they use something called as pulsars. So pulsars are a certain stage of stars. So there are certain these are stars in a certain stage where they emit light in a frequency. For example, there are second pulsars also. So for 1 millisecond, they emit light in 2 times, right? So for example, you can see in the left side, this is one pulsar. So pulsars have light being emitted from the poles, right? So for every millisecond, they rotate around themselves. So these are very huge stars that are rotating very, very, very rapidly. That can act as a lighthouse in space, right? So if you have three different pulsars, you can point to a certain region in space that you are there, and you can say, I am at this particular point because I have these three pulsars in a particular configuration. That is how deep space navigation is done, and that is how navigation across human space programs, if you're going away from Earth, and voyages, all of that is done. So this is also one of the main research topic that is happening. Now, we have covered in a very detailed or an abstract view of all different research that is being done. An interesting thing that whenever you speak about space is astrobiography, life in space. Is there life in space? How do we understand? So very, very big research topic is exoplanets. So if you go to any physics department or an astronomy department, what happens is most of the time you will find some person working on exoplanet discovery. So what is exoplanet? Exoplanets are basically planets that are there for different stars, not stars like sun, but for some other stars, let's say even in Milky Way or even in other galaxy. But in other galaxy you cannot resolve to a very big distance. So stars that you can see in our galaxy that have planets, so how can we detect that, right? So that is a very big research topic. And if you see study about it, there's a concept called as Goldilocks zone, right? So what is Goldilocks zone is that if you want to detect life like Earth's life, right? So Earth's life is made of most of the organic compounds, water, etc. So if you have carbon, if you have water, you can have life, right? So there is if you have a star, there is a region around star where water can exist, okay, in liquid form, right? So that is called Goldilocks zone, right? So there is a thin region around the star, right? So this is called Goldilocks zone. If you are closer than that zone, your water is going to become gas. If you're farther from than that Goldilocks zone, the water is going to freeze, right? So that is called as habitable zone. So if you so often you see that okay, this planet is habitable, etc., etc. in news, that means that okay, the planet is in this Goldilocks zone. That's it. Now, how do we detect these exoplanets? So all, if you have telescopes, you can see stars, right? And even in stars also you can do spectroscopy and you can see what are the elements that are there. For example, if you take sun, right? Sun has a lot of hydrogen and helium, almost every star has. So you can, from the ratio of these elements, you can find out which stage of the life cycle of star that this is, right? So stars have a life cycle. If you don't know about that, you can read about it, right? So by observing these particular ratios, you can estimate okay, the star is in this particular stage, etc., etc. But how do you know about planets? Because stars itself are very, very huge and very, very small in sky. With the even in telescopes also, you cannot clearly see how a star is there in space. You can just see a dot and some light coming from it. And how do we detect planets is really interesting, and these are some of the methods. One interesting thing is transit timing variation. So what happens is, as the planets go around the star, if you see the light that is coming from the star, the light is, for example, if you're observing the star, there's a certain brightness that is coming, right? And once the planet comes before the star, the brightness actually decreases because this planet is actually blocking some amount of light, right? So if you see the brightness curve, the star brightness is constant, but when the planet comes before the star, it decreases, the brightness decreases. And the brightness is less as long as the planet is before the star, and once the planet again goes from the field of view, the brightness actually increases. So from this time period, you can decrease in the brightness, you can guess what is the orbit of this planet around that star and how big is this planet, right? So this is one of the thing. The other thing is radial velocity. So for example, if you take sun and earth, these are gravitationally bound bodies, and Earth and Sun revolve around barycenter, something called a center of mass. And for a bigger system, it's called as a barycenter. So even Sun is also moving very slowly, right? So stars also sort of move around this barycenter. And if you see the wavelengths, right? So star has a particular, a black body radiation and emissions. Now, what happens is if the star is moving in your field of view in a radial way, these because the star is moving, the wavelengths are going to be shifted, right? The wavelengths are going to be shifted because of Doppler effect, right? Because a moving source always shifts your wavelengths, right? So obviously there's going to be radial relativistic Doppler shift, but these are going to be shifted. And when these are shifted, you can understand that okay, stars are moving. So because based on this movement, you can analyze okay, there's some amount of planet in this system. And the other concept is called microlensing. So gravitational lensing happens because of relativity. You can read about it. So these are some of the topics that you can note down and read after this talk. So microlensing is when you're actually observing a background star, right? So for example, there are two set of stars, right? You are actually observing background star, but you cannot see the background star, but this middle object acts as a lens, right? So it actually diverges the light and actually shows you the background star. So this is what is basically gravitational lensing. So if you have a planet, what happens is that the planet also acts as a lens, and you can see a little bit of a blip that is coming when you are seeing the background star. So that is how that is what I have shown in the slide also. And astrometry is when you are actually seeing the position itself of the star that is moving, that I told you about the Doppler shift that you observe from the spectroscopy. But you can actually, if you in the sky itself, you are able to see that the star is moving a little bit, then you see that okay, there's a very big amount of planet that is there. And direct imaging is another way. Direct imaging rarely happens because you cannot even see the stars, how you can see the planets. So these are some of the exoplanet detection methods, and this is how you, in the news all the time, you are able to see okay, we discovered 611 planet B for this star, etc. So mostly it is transit time variation or radial velocity based exoplanet detection, right? So I think that I have covered most of the topics, you know, trending topics in scientific research that we do through space, right? I think that's it from my side because I have covered most of the topics that I have. Some of the interesting other topics, like if you wanted to study, is like space weather, space debris, star life cycle. So if you talk about stars, they have different life cycles, right? So if you talk about neutron stars, pulsars, quasars, supernova, how the stars form, right? All of this is really interesting, and this is all really fundamentals. As you go in the career, you will sort of learn more things about what is the current things that are happening, right? I think that's it from my side, and I think you will all have a lot of questions, and I'm open to questions from now. I think we can take some questions. No, Rohan?
Just a second. Yash, are you there?
Hello. Yeah, hi Rohan.
Yeah. So, should we take the Q&A session right now, or are you going to take over the session?
No, no, we can take the questions right now.
All right,
No
all right,
problem.
all right, all right. All right. So, yes, yes, guys, you can ask your questions. I guess there are some of the questions in the chat. I guess I'll just read the questions and you can answer. That would be fine. All right. So the first question is, I guess, from Georgina. That is, what satellites are orbiting around Mars? This is the first question that we are having.
Okay, so there are a lot of satellites, guys. Most of the countries have sent. You can look at the list. It is available on Google. So yeah, one thing that I can say is we have MOM and we have MOM2 that is coming up, and from USA you have even Viking rover and all of that. So that's a list that you can look at. Yeah, next I'll just go to the next question regarding geology. Can you give an example for a potential landing site for Martian human presence, as in the case to place an habit? So for when you consider Mars, right, most of the surface is actually very uniform and it is having most of the minerals that has iron, right? So there potential landing site, for example, if you wanted to talk about it, you will have to focus mostly on your landing or your spaceship design, etc. But there's no preference for potential landing site. If you really wanted to understand, like for example, there's like large polar ice caps for Mars. So if there is a research component for landing that you wanted to research those ice caps, then you can talk about polar ice caps. But when you land near poles, then you are not going to get a lot of solar energy. So whenever you are going to other planets, you are mainly dependent on solar energy, solar panels, etc. When you don't want to be dependent for a large time on fuel, so then you have to obviously go to a place where there's good amount of solar radiation that is coming. One more thing is, if you wanted to talk about fuel, most of the fuels that we have on Earth are not going to work on Mars because of combustion, right? So basic physics of fuel is that you need to have oxygen to your for your engines to work. You are not going to use a basic fuel, so there's going to be some different amount of propulsion, like electronic propulsion, and light based propulsion that have to be used. So based on these different parameters, you can choose a landing site. What next question goes about, what about atmosphere of Mars? That is, does it have layers of atmosphere like Earth? Sure, they every planet will have a certain atmosphere, if not a thick layer. Even for Moon, there's certain molecules that are bound to its own gravitational pull. For Mars also, it has a atmospheric layer, but it is not similar to what it is of Earth. As you mentioned, L2, Aditya L1. Okay, so I'll just go to my presentation. So these L1 and L2 points, these points are basically what these are called Lagrangian points. So I'll just go to the presentation if I can. 1 second. I will show you the diagram for this Lagrange points. So what these Lagrange points do, right? So if you place some object in those point, right, it is not going to move, right? So because of the gravitational compensation that all different bodies are doing. For example, if you place a point in L1, sun is going to give a equal amount of gravitational pull as that of Earth. So that L1 point is going to be staying constant. If the Earth is moving somewhere, the L1 point is also going to move. So this line that is there is going to be fixed even if you put it in L4, L5, L3, and L2. So if you wanted to put something in L2, that has to be something that does not want to see sun. It is away from Earth and sun, etc. But if you want to put something in L1, What does that mean? It wants to look at sun, and it does not want to mostly focus on earth if it is directly looking at sun, right? And when it is at L1, it is also having a good amount of field of view on earth. So if you have some amount of ground stations on earth, you can frequently contact that L1 and take the data. And it is, again, it can always look at sun. So Aditya L1 is designed in that way that, okay, if we put our satellite around sun in that L1 point, what is going to happen is it can have a good view of sun at all the time, and also earth. And this ratio and this line is always going to be focused, and it is fixed, right? So it is a satellite around the sun, but with respect to earth, the line is fixed. So that is Aditya L1. And what Aditya L1 is going to study, there's again multiple instruments, most of them spectrometers. What is the sunspots made of? We want to study the magnetic fields around sun, etc. and etc. So that is for Aditya L1. Coming back to the questions, are pulsars and quasars similar? They are not similar. Pulsars and quasars are really different. Pulsars, from the name itself, you can understand that they are pulsating stars, and also very, very distant from regular red giant stars. Quasars are again different. Quasars are basically made of magnetic field oscillations, and pulsars can actually emit these electromagnetic pulses. Sir, does ISRO have a place for astrophysicists? If yes, how can one get in? Sure. So ISRO has multiple centers that do astrophysics research. Most of the time, if you wanted to become an astrophysicist in general, not speaking about ISRO, you would have to do your PhDs in astrophysics. And ISRO, you can get in by the entry to ISRO is after you do your BTech, you can give an exam and join ISRO. Also, if you are interested, you can do your PhD and again join ISRO at a senior level. Is it possible to use asteroids to travel through space? Definitely, it is possible. So if you asteroids are basically some bodies that are rotating around sun, right? So if you land, like for example, Rosetta is there. If you are landing your mission on Rosetta, like on an asteroid, it is going to transfer you from point to point. But it depends on again how you want to lift from that asteroid again. You have to launch right from asteroid again to go to another place. So that is something that you have to discover and invent. I don't think such missions exist now. How does satellites destroy asteroids in space? So asteroids are really big objects, right? So the things that are coming to Earth are mostly called meteors or meteoroids. And there are federal agencies that focus on sort of interacting with these meteors and destroying them. Satellites don't do it. Satellites basically focus on what these meteors are made of and studying the geology and the composition of asteroids. How do you destroy them is basically there are some recent instruments that are ground based. So what they do is they emit very high powered lasers, which can actually fragment these asteroids or meteoroids. So what happens is if you focus this high power laser on those meteors, what happens is these meteors get fragmented. Again when they come to Earth, they burn, right? So yeah, so that's how that is done. I've not seen destroying asteroids in space. Asteroids are really huge objects. I don't think humans can do that. One way that I can see is exploding nuclear bombs and etc. I've read some paper regarding that. You can also read about it. What is the exact difference between the core job profile of a data scientist and astrophysicist? Okay, so data scientist in ISRO, like for example, if you talk about a data science job in ISRO, you are getting data from satellites and space telescopes. Satellites can be n number. You can do data science on Earth, phenomenon, agriculture, water, atmosphere, etc. You can also analyze the data of space telescopes to the exoplanet or stellar dynamics, etc. So all this is data, right? And you are sort of trying to get these patterns from this data to identify phenomenon, scientific phenomenon. So data scientist is a quite catchy name, but if you're doing pattern recognition on data, you are a data scientist. So most of the guys who are doing satellite imagery analytics or data analytics are data scientists. Astrophysicist is like a guy who knows physics or astrophysics and is trying to study something about a space phenomenon or astronomical phenomenon. So astrophysicist is also a kind of data scientist because he's analyzing the data and is using the methods that you general data scientist uses. So there is no different job profile based difference. So can you tell any resource to study electric propulsion system in detail? Electric propulsions again are recent innovations. So, for example, if you wanted to see a finished product, you can look at Indian companies are also there like Bellatrix Aerospace, Dhruva Space, which are focusing on electric propulsions. But if you wanted theoretical electric propulsion detail, at the moment I cannot tell you some of the books, but I can go back and get back to you. You can always contact me on LinkedIn. The slides I think they will share. I have given my LinkedIn profile. You can again contact me and I will get back to you with some of the books that you can read to get more information about electric propulsion. Yeah. Any more questions you can ask? So a scientist at ISRO is a guy who has, for a fresher, if you are finishing your BTech and you're clearing your exam, you can join as a scientist at ISRO. And once you are joined as a scientist and ISRO, your life is going to be different. So till one time, till you become a scientist, you may be interested in one thing, but after you join ISRO, you will get to learn a lot of different things, and your uh, ideology changes. Then your interest will change. So till you become a scientist, all I can say is study good and study in depth. Right. So if you want to clear even ISRO interviews, also they're going to try to gauge your conceptual understanding. If your conceptual understanding is good, obviously you can become anything. So focus on science and good study of whatever you're interested in, and then I think you can become a great scientist. How frequently do comets pass the Earth? A lot of comets actually pass Earth every day. But the thing is, can you see them from Earth? That is the important thing. So there are comets that are not having a lot of brightness, but there are comets like Halley's Comet, which have a very, very huge brightness, and you can see them in space passing through very, very slowly, right? So, yeah, so frequency, almost every day, I think you can see a comet that is like passing through Earth, like passing through your visible area, but it depends on with what you are seeing it. What are the prospects of finding life beyond Earth, and what methods? As I told you, when you talk about life beyond Earth, so another exoplanets are anyways there, and you can also research on what is the atmosphere of those planets, etc., from the spectroscopy and the radio Doppler effect that I told you. The other component is that it's a really philosophical search. Like, for example, if you talk about Voyager, so there are some phenomenon in universe that are fixed across the universe. Okay, like for example pulsars, right? So pulsars are fixed, and the philosophy is that most of the people who are doing research, for example, if you take an alien life, for them also pulsars are same, right? So they can be used as navigational guides. So the philosophy is that they will also be using those pulsars as guide. So we, whenever we communicate with aliens or extraterrestrial life, we give this pulsars information. So these are standard phenomenon. Like that, the one more phenomenon is 21 centimeter line. So these are some terms that you can read after this talk. So 21 centimeter line is a emission of hydrogen. Okay, when so in hydrogen you have 1s1, right? So one proton, one neutron, one electron, one proton, one electron, right? So what happens is that if your electron spin up is going to convert into spin down because of the stability, it is going to emit a radiation, right? And even for the deuterium, if you have a neutron there, again it is going to emit radiation, right? So these are standard emissions that are fixed across universe, and this is a radiation that always happens, right? So spin up, spin down, spin up, spin down. These hydrogen atoms always keep on absorbing this 21 centimeter line and keep on emitting this 21 centimeter line, right? So this is something that you can see across the universe. If you see stars, you can see 21 centimeter line. So this is also something that we use to communicate to extraterrestrial life if they are there or not there, these are some of the phenomenon that we study and we sort of try to communicate. um, how do we actually figure out the galaxies in a deep space image full of different bright sources? So all this is something that comes out of computer science. So if you're doing computer science and image processing, telescope images are basically images, right? So what happens is if there are two galaxies that are mixed, right, and if you plot a brightness profile, what happens is that to the center of the galaxy the brightness is going to increase, again decrease, and the other galaxy again increase and decrease. So if you plot it, you're going to see two peaks, right? So you can separate them at the middle, or the frequency graph that you can see, or the brightness graph that you can see, and you can identify them as two different galaxies. Please share your LinkedIn profile link. On LinkedIn, you can search for my name, Radhakrishna Kavluru. You can find my profile. The link is already there in the slides that have been attached in the uh, chat. You can download the slides and also have a look at the first slide. The link is there and there. Any other questions, guys? What is clearly a black hole? Okay, this is also interesting. So as I told you, stars have life cycle, and what happens is that if you take a star, right? So I'll tell you. So the basic of how stars evolve is that stars have two components. Okay, one thing is stars have radiation that are being emitted from nuclear fission and fusion reactions, right? So take a sun. There's a lot of nuclear fission and fusion that is happening on star. So radiation is coming out. But what happens is that the star has a lot of hydrogen and helium, mostly hydrogen, right? So because of star's gravity, hydrogen wants to come down. The gravity pulls hydrogen down, all the gases down. But what happens? There's a lot of light that is coming out, a lot of radiation that is coming out. This radiation is pushing hydrogen outside. So the balance here that is important is that radiation pressure outside, gravity inside is what balances a star, right? And what happens is that as the core of the star slowly loses its fuel for fission and fusion reaction, gravity overcomes the radiation pressure, and the gases slowly come closer, and finally when gravity wins, what happens is that there's going to be a sudden collapse of all the gases into the core of the star, and there's going to be a huge explosion that's called as a supernova explosion. Okay, now all stars don't have to go through supernova. Some stars actually end up as neutron stars. So neutron stars are stars which are highly condensed. So in my fist size, there can be a very huge amount of star. All the neutrons are tightly coupled, right? So these are neutron stars. There's going to be some stars which can end up in supernova, and then there's going to be some stars which can end up as black hole. Black hole is when the gravity is so intense that even light cannot escape from that particular core of star, right? So that phase of stars is called black hole, where light also is not able to escape from that gravity. So as I told you, fight is always there between light, radiation pressure, and the amount of material that is there around star. But even when the light is also not escapable from that gravity, you can find a black hole. So what is the scope for pursuing their bachelor degrees? Like BE is also considered similar to BTech, I think. For BCA, I have not seen any notifications. So I think BTech is necessary, but for some other roles like research scientists and product scientists, BCA is also considered, but that you have to confirm from the website. BTech, I can guarantee there are a lot of posts. For BCA, the another standard thing that people do is after BCA, they sort of try to do MS and PhD. So then again, you can join ISRO. MS also, there are some rules I think that you can join ISRO, but for BCA, I don't think there are any notifications. You can confirm from the website. As I said, black holes are made by collapsing of stars, but not every star creates a black hole. Yes. So is the limit of no. So when you talk about limit of our space-time fabric, it is very deep. So all that we are talking about is like relativistic physics, but quantum physics so when you talk about limits, quantum electrodynamics and quantum physics takes its place, and the physics at quantum level is really different. So there's no sort of limit at the moment. If you talk about limits, right? If you talk about space limit, something called as H cross, Planck's constant, and there's called as something called as a Planck space. The minimum amount of space that you can take is called Planck space, right? That is considered as a space limit, right? In the current understanding of physics, so everything is quantized. Space is quantized, time is quantized, energy is quantized. So in that way, there's something called as a Planck space, the amount of smallest amount of space that you can have, that you can read about. But that is about the current understanding. We when it the science goes to a minuscule scale, we cannot really understand what is happening. Still, everything is in the research phase. Comets that are passed through Earth, which is visible to our naked eyes, will they pass with a constant amount of speed, or they okay? So comets are similar to planets. They orbit around sun, so their speed will definitely vary. But for a normal day that you can see with your eyes, the speed will be constant because the orbit is very small for the duration that you are seeing. But on a larger scale, yes, their speed will be varying when the comet is really close to sun, and when the comet is really far away from sun, the speed will vary because the orbit is really polar, and you can understand even Earth's orbital speed also is not constant because orbits are elliptical. Yeah.
That was a great session, sir. The way
Yeah.
you answered all the questions are also good. It was just amazing.
Thank you.
Yes.
Thank you.
Yes. Yes.